For now, I want to introduce Ying Tong from Coin Company, who's going to be telling us about the latest developments in Halo2.
Hello. Hi, I'm Ying Tong. I'm a core engineer at the Coin Company, and yeah, I'm bringing you the latest developments in Halo2. So the Halo paper was published in 2019, and we came up with Halo2 in about 2020 that basically replaced Sonic with Plonk. And ever since then, we've just been implementing it, we've been learning, we've been finding mistakes and bugs, and we've been seeing adoption in other community projects, such as the zkEVM. And so I'm here today to share what we've worked on and what we're looking forward to. So an overview of the Halo2 proving system is basically in these 7 steps. And we probably won't have time to go through all of them. I'm going to spend the most time on the first step and the last step, because these are the ones that we've basically found the most interesting. And the first step is the arithmetization. This is a topic that has been discussed in previous sessions, such as Kimchi and Vampire. And yes, and I know this is like the 7th or 8th time we've seen the vanilla Plonk constraint. I show it here to demonstrate that basically it's a single constraint whose selector values you can tweak in order to express different constraints. So you can tweak it to be an addition expression or a multiplication expression. And this is a different paradigm from UltraPLONK. UltraPLONK introduces custom gates. So for each expression, you can define a bespoke gate. And then later on, you can linearly combine these gates with powers of a random challenge. And we visualize UltraPLONK in this sort of matrix format, whereby each gate can be enabled or disabled on a row in the matrix. So how ECC's UltraPLONK differs from Kimchi or Vampire is we basically expose all the degrees of freedom to the circuit writer, and we make it entirely customizable. And so the mental model of our circuit is very visual. It's rows and columns, and the circuit writer has full control, basically, over the configuration and over every single assignment in this matrix. So we know this already. Each cell contains a value from a finite field. And each column corresponds to a Lagrange interpolation polynomial that evaluates to that cell's value at omega to the power of I, where I is the row. And omega is, of course, the primitive nth root of unity. It's our multiplicative subgroup. So because we expose so much freedom in the circuit configuration, it's important to understand the different types of values that go into the circuit. So we have different kinds of columns. The first kind is the instance column, and these contain values that are shared between the prover and verifier, for example, public inputs. The second kind of column is what we call the advised column, and these hold the prover's private witness values. So the instance and advised columns change with every proof instance, whereas the last type of column is the fixed columns, and these are pre-processed at keygen. They define the circuit, and they're hard-coded, and they never change. So I'm going to show an example of an addition custom gate that basically concerns itself with those 3 advised columns on the same row. And with UltraPLONK, you have the freedom to define the shape of your gate. So for example, if I wanted to access an offset in the next row or the previous row, I could specify that in my constraint. And as the circuit writer, I'm responsible for choosing the shape of my gate that is the most optimal. So for example, in Zcash's orchard circuit, we've had multiple gates shaped such that we can stack them and fully pack the circuit. And we all know that how these offsets work is simply by shifting the evaluation point by omega, the primitive nth root of unity. So yeah, now this introduces some kind of tension, because on the one hand, we need to think of gates locally. We need to think of them in terms of relative offsets. But on the other hand, we want to lay out our global circuit as optimally as possible. And we want to automate that laying out process as much as we can, while retaining control over the local offsets. So to deal with this tension, we've introduced the abstraction called regions. And what a region is basically a self-consistent block, a self-consistent area of assignments that are defined relative to the same global offset. So you can think of it in terms of all the cells in one region share the same 0. And what this means is that one region is independent from another, meaning that if I'm within one region, I'm completely unaffected by offsets, by gates, by assignments in the other region. And I can basically move regions relative to each other and rearrange them and pack them however I want without worrying that my gate assignments will be affected. But this region abstraction introduces another problem, which is how do we maintain some kind of link between regions? If we're moving them around freely, how do we still ensure that values across regions are consistent with our constraints? Oh. Before that, I want to show why being able to move regions freely is good. So what it comes down to is your layouter strategy. We're giving you the freedom to move regions, and how are you deciding to move them? So this is our simple layouter that just lays out regions one after the other as the developer assigns them. Whereas this, the exact same circuit, the exact same regions, this is our dual pass layouter that does the first pass to get the shapes of the regions, and then the second pass to vertically pack them. And just this one change in our layout strategy reduces the circuit by an order of magnitude, by a power of 2. And this reduces like your FFTs, this reduces everything. So the power of the layouter and the region, it gives the circuit developer so much freedom and so much freedom to optimize. So yeah, but as I was saying, between regions, we still want to maintain some kind of relationship, some kind of consistency. And what you see on this diagram is all the equality constraints in the orchard circuit that are tying one cell to another. So every line there is basically an equality constraint enforcing that two cells have the same value. And with equality constraints, you can then link together cells from different regions, because equality constraints are global, and they will be enforced even if you move regions around. The last sort of setup in our UltraPLONK circuit is the lookup argument, and this is basically This is basically a relaxed version of the permutation. It doesn't enforce a specific permutation, but rather it just enforces a subset argument. So, for example, here we're enforcing that values in those two columns are a subset of values in our fixed table. And one nuance of the lookup argument is that it has to hold true on every single row. So when the lookup argument is not enabled, 0, we need to actually look up a default value in the table so that the lookup argument still passes on that row. And it's come up in certain talks before. Right now, in our implementation, we only support fixed columns for lookup tables, and this is a decision. This is a decision we made for safety. Basically, if the lookup table is fixed, then we can pre-fill it fully with a default value. However, our partners have come up with use cases that actually require dynamic lookup tables. It requires basically the ability to look up witnessed values as well. And this is one of the areas we're actively working on in this issue. We're writing up an API, so feel free to contribute if you have opinions. So yeah, the Synsomia gadget is one example where we heavily use the lookup argument to basically look up fixed generators that are used in the Synsomia hash function. And what you see here are printouts of the gadgets we've written. We've written a gadget for the Poseidon hash function as well. And elliptic curve cryptography, as well as an experimental SHA-256 chip. So the point of these gadgets and chips is that they are meant to be reusable. They are meant to be modular. And we do want them to be primitives that our other projects can consume. I do want to mention that the ECC circuit in particular, it makes use of lots of manual optimizations. So for example, for fixed base scalar multiplication, we actually witness the coefficients of a Lagrange polynomial that interpolate to the x-coordinate of the fixed base. So this is an example of a non-trivial optimization that could only have been done with direct manual control over the circuit. And if we were to explore moving to an IR, perhaps we could encode this strategy as one rule or an alias in the IR. Yeah, but currently we've made full use of the freedom we've been given in the API, and we've fully optimized the Orchard circuit. So that being said, we are actively exploring moving to the next phase of this API. So we're looking at DSLs and we're looking at IRs. There's an issue, add an API to construct a Halo2 circuit from a set of constraints. So Strat just wrote that issue, proposing a strategy to integrate Halo2 with Vampire. And we are always trying to just improve the floor planner ergonomics and make our APIs more usable. So if you have a wish list or features that you would like to see, just come talk to me or open an issue on our GitHub. So our arithmetization has been used in the zkEVM Community Edition project. And basically, we found that, our arithmetization has been expressive enough to support EVM opcodes. And it's been expressive enough to do things like switching on gates, and also to enable linking different subcircuits through lookup arguments. So yeah, I think the Scroll Tech gave a great talk about the zkEVM Community Edition earlier, and I encourage all of you to take a look. And basically, I've been inspired by how they've taken this API and pushed it to its limits. And there are lots of great optimizations coming back from the zkEVM project. So optimizations like introducing a multi-stage prover, meaning that the prover that can actually commit in the first stage and query randomness in the second stage. They've also introduced various optimizations like at low level, like FFT assembly. So it's been a great collaboration with the zkEVM project. Yeah, so that's our arithmetization. How am I doing on time? I
think you have like 8 minutes.
8 minutes, okay. 8 minutes. In that case, I'm going to skip over the intermediate steps. These steps are describing how we go from our polynomial constraints to basically some polynomial that we can put into our inner product argument. And the inner product argument, so up to this point, we've implemented all of these, and this will be deployed in our next network upgrade. So our inner product argument is what we use to construct an accumulation scheme. And the accumulation scheme is how we achieve recursion. So Halo2 is a recursive proving system with no trusted setup. But the recursion part of Halo2 will not be in our next network upgrade. So we are currently implementing the recursive API. The inner product argument is amenable to an accumulation scheme because it has a cheap check and an expensive check. And basically at each accumulation step, we only perform the cheap check, and we delay the expensive check to the final decider. In effect, we amortize the expensive check across a whole series of cheap checks. And the accumulation scheme, I don't know if people here are familiar with IVC, incrementally verifiable computation. Let me put my glasses on. So yeah, an IVC proof consists of both the snark proof and an accumulator. First of all, we compute a state transition, the state transition function. That's the application logic of our snark. Then we accumulate the inputs from the previous proof instance into our accumulator, and we produce a new accumulator. And this is the job of the accumulation prover. And we also have an accumulation verifier that's checking that the accumulation was done correctly. So the accumulation verifier and the state transition function are what we call what we prove in the snark prover. And the proof of those two circuits gives us our next proof instance, pi I plus 1. So we continue this for as long as we want until we reach the final stage, which is the decider. And this decider D is what's going to perform the expensive check. The expensive check is basically the check that our accumulator that we've been just providing thus far is actually well-formed. And also in our final, with our final decider, that's a snark verifier that runs the final snark verify, that checks the final snark proof. So with this IVC scheme, we're planning to apply it to Filecoin, and we have a collaboration with Filecoin that's underway right now. So Filecoin basically has a problem with, they have too many proofs on-chain. So for each sector, each Filecoin sector, they need 10 snarks. Right now it's Groth 16 proofs. They need 10 Groth 16 proofs to prove one sector. And basically, there is a limit to how many of these Groth 16 proofs you can stuff into a single block. So they're running out of space in their blocks, first of all. And then secondly, even if you could put it all into a block, you would run out of time, or you would run out of gas trying to verify it. So we need to cut down on the proof size, and we need to cut down on the verification time. So the plan is to accumulate all these proofs into one recursive proof, and then just submit that to the block. And we only need to verify one proof. Yeah, that's all I have. Thank you.
Great talk. Are there any questions? Yeah, you got one.
Hey, great talk. I had a question about the last slide. So if they have Groth 16 proofs, how are they using accumulation with those?
Oh yeah, now that's a great point. So right now, Filecoin is rewriting their circuits using Halo2.
Okay.
So they're not, these are not Groth 16 proofs anymore. They're Halo2 proofs.
All right.
Yeah.
Anyone else have some questions?
I guess another question about this slide. So you're replacing 10 Groth 16 proofs with a single Halo2 proof at the end, right? So like how much space are you saving by that? Like how much smaller is the single Halo2 proof versus 10 Groth 16 proofs?
Yeah, that's a great question. So I think right now Filecoin has deployed something called Snark Pack, yeah, which actually already does proof aggregation. But they even with Snark Pack, they run into a limit to the number of proofs they can aggregate. Whereas with Halo2, it's like basically unbounded. Yeah.
Makes sense.
Yeah.
Very cool. Anyone else? I think if not, then thank you so much.
Yeah.
Cheers.